We are going to graph and transform the function f of x equals e to the x. So here is a graph of f of x equals e to the x. It looks like a regular exponential function. We have a horizontal asymptote at y equals 0 or the x-axis. We can see a y-intercept at 0, 1. The domain is all real numbers, so it goes from negative infinity to positive infinity. So showing the different ways we can represent the domain. We have interval notation. We can write x as the element of the real numbers, or we can write the set of all x's such that x is an element of the real numbers. And then the range goes from 0 to infinity, or y is greater than 0, or the set of all y's such that y is greater than 0. So these are the basic attributes for the parent function f of x equals e to the x. There is no x-intercept, just a y-intercept. Okay, so now let's look again at the graph of y equals e to the x, along with y equals 2 times e to the x, y equals 1/2 e to the x, and y equals negative e to the x. So we can see all four of these graphed on the same coordinate plane here. Reminder of the attributes of the parent function. We've got a horizontal asymptote at y equals 0. We have a y-intercept at 0, 1. We have a domain of all real numbers and a range of all the y's greater than 0. In red, we can see the function y equals 2 times e to the x. This is a vertical stretch by a factor of 2. The y-intercept does change. The horizontal asymptote stays where it is. But now the y-intercept is 0, 2. We can see that on the graph. But the domain and range stay the same. But now in blue, we can see the function y equals 1/2 e to the x. This is a vertical compression. And again, the horizontal asymptote, domain, and range stay the same, but the y-intercept does change. And the y-intercept for this vertical compression is 0, 1/2. Finally, in green, we see y equals negative e to the x. This is a reflection over the x-axis. The horizontal asymptote is the same, but now the y-intercept reflects down to 0, negative 1. The domain stays the same, it's all real numbers, but the range changes to negative infinity up to 0, or the y is less than 0. In summary, for vertical stretches, compressions, and reflections, functions of the form y equals a times e to the x, if the absolute value of a is greater than 1, we have a vertical stretch. If the absolute value of a is between 0 and 1, we have a vertical compression. And if a is less than 0, if a is negative, we have a reflection across the x-axis. Okay, we'll look at the parent function again, y equals e to the x, but this time with y equals e to the x plus 2 and y equals e to the x minus 4. We can see all three of those graphs on the same coordinate plane here. And a reminder about the attributes of the parent function. We have a horizontal asymptote at y equals 0. We have a y-intercept at 0, 1. We have a domain of all real numbers. We have a range of y values greater than 0. Here in red, we can see the function y equals e to the x plus 2. This is a vertical translation up 2 units, or shift up 2 units. So our parent function, we saw the asymptote at y equals 0, and now for the red function, the asymptote shifts up 2 units. So the horizontal asymptote is at y equals 2. The y-intercept also shifts up 2 units to 0, 3. The domain remains the same, but the range changes to be all real numbers such that y is greater than 2. Here in blue, we see the graph of y equals e to the x minus 4. This is a vertical translation down 4 units, or shift down 4 units. So again, the horizontal asymptote is shifting down, this time to y equals negative 4. The y-intercept is shifting down, this time to 0, negative 3. The domain stays the same, all real numbers, and the range changes to all real numbers such that y is greater than negative 4. So in summary, for vertical translations, if we have a function of the form y equals e to the x plus d, if d is greater than 0, we are shifting up the absolute value of d units. If d is less than 0, we are shifting down the absolute value of d units. Okay, we're going to look at the graph of the parent function again, y equals e to the x. This time we'll look at it along with y equals e to the x plus 5 and y equals e to the x minus 3. Here we can see all three of these graphs on the same coordinate plane. And then just a reminder about the attributes of the parent function. We have a horizontal asymptote at y equals 0, a y-intercept at 0, 1, a domain of all real numbers, and a range that goes from 0 to infinity. Here in red, we see the graph of y equals e to the x plus 5. And this is a horizontal translation, left 5 units, or shift left 5 units. So the domain remains the same, the horizontal asymptote remains the same. The y-intercept changes, and the y-intercept changes to 0, e to the 5th, because if you remember, to find the y-intercept, we substitute 0 in for x, so y equals e to the 0 plus 5, which is e to the 5th. So the range also stayed the same. And then here in blue, we see the graph of y equals e to the x minus 3. This is a horizontal translation or shift right 3 units. And again, the only attribute that changes is the y-intercept. This time it changes to 0, 1 over e cubed. And I found that, again, by substituting 0 in for x, we have y equals e to the 0 minus 3, which is e to the negative third power, which is the same thing as 1 over e to the third power. In summary, for horizontal translations, if we have a function of the form y equals e to the x minus c power, if c is greater than 0, if c is positive, then we are shifting right the absolute value of c units. And if c is less than 0, we are shifting left the absolute value of c units. Okay, so we've been looking at y equals e to the x. In a few sections ago, we looked at y equals 2 to the x and y equals 10 to the x. Let's look at all three of those combined on the same coordinate plane. So we have y equals e to the x here in black. It's the middle graph. The red graph, y equals 2 to the x, is the one that's all the way to the right. Y equals 10 to the x is this blue one. And just to look at the bases, we have e, we have 2, we have 10, and e is between 2 and 10. Remember, the general form for an exponential function is y equals b to the x, where the base, and we've looked at e, 2, and 10, where the base is greater than 0. These are all positive. And the base does not equal 1. None of these equal 1. But larger b's, so like if I'm looking at y equals 10 to the x, these functions grow faster. And if b is greater than 1, remember this is an exponential growth function. All three of these are exponential growth functions. But if b is between 0 and 1, we have an exponential decay function. Let's look at one of those. So y equals 1/2 to the x power. I can plot a few points. I still have my y-intercept of 0, 1. We have negative 1, 2. We have negative 2, 4. Negative 3, 8. We have 1 comma 1/2. 2 comma 1/4. And sketching in my decay function, here it is.